Good morning, everyone. Good morning, madam. Today I am showing about my presentation. The presentation structure is the presentation explains the motivation for investigating the data set, the data handling process, the critical evaluation of methods, the key findings, the working application, and final reflection on limitations, recommendations, and version control. I now share my screen. This is a presentation overview, project overview, dataset selected from 4 Beijing monitoring stations, analysis focused on PM2.5 related pollutants and meteorological variables, project stages, data selection and handling, exploratory data analysis, model building, application development, version control and reflection. Motivation for investigating the dataset. Rationale for dataset selections. Air pollution is a major environmental and public health issue. PM2.5 is a critical pollutant because of its harmful health effects. Beijing provides a large, detailed, hourly monitoring dataset. The dataset includes both pollution and weather variables. Important aspects to explore. Differences between urban and suburban monitoring stations, seasonal variation in air quality, hourly pollution behavior, relationships between PM2.5 and other pollutants or weather conditions, accepted outcomes, identification of a spatial and temporal pollution patterns, better understanding of the factors associated with PM2.5. Development of an interactive application to communicate results clearly. Data handling. Selected monitoring stations, urban stations, Dongxi, Guiyuan, suburban stations, Changping, Huaryu. Important process. 4 CSV files imported into Python using pandas, file shapes and schemes checked before integration. Each file contains 35,064 rows and 18 columns. Integration process. New date time variable created from year, month, day, and hour. Station labels retained from comparison. Files merged into one data frame, air data. Final dataset size 1,40,256 rows and 19 columns. Challenges and resolutions. Need to confirm schema consistency before merging. Need to preserve timestamps correctly. Need to ensure station identifiers remained accurate after integration. Figure 1 is the combined dataset and station counts. Figure 2 combined dataset preview after merging 4 station files. Critical evaluation of a data cleaning and pre-processing. Initial data issues we have. Missing values were present in several pollutant variables, especially CO, NO2, O3, PM2.5 and SO2. Pollutant distribution showed strong positive skews. Several variables contain extreme upper end values. The no column had no analytical value. Cleaning decisions. Removed the number column, checked duplicate rows and found 0 duplicates. Filled missing numerical values using the median. Filled missing categorical values using the mode. Justification of pre-processing decisions. Median imputation was more robust for skewed pollutant variables with outliers. More imputation preserved the most frequent category and categorical fields. Removing non-analytical columns improved dataset quality for data analysis and modeling. These steps produced a complete and structured dataset for larger stages. Feature engineering. Created season from month, derived day of week from date time, created ease weekend indicator, created PM2.4 category for air quality grouping. This is the preview of engineered features. Critical evaluation of a EDA methodology. EDA approach to use unvariate analysis, distribution of a pollutant and meteorological variables, outlier analysis using box plots, bivariate analysis. PM 2.5 was a temperature, PM 2.5 was wind speed, NO2 was O3, PM 2.5 by station and season. Multivariate analysis, correlation heat map, pair plot, station season heat map. Justification of EDA method. Unvariate analysis revealed skewness and extreme values. Bivariate analysis highlighted key variable relationships. Multivariate analysis is showed overall correlation structure. Combined use of charts improved understanding of both the data and the domain. Critical comment. Using several EDA methods were more informative than relying on a single chart type because air quality patterns vary across time, space, and pollutant interactions. Key finding from analysis. These are the distribution station and this is the distribution by season. Distributional findings. PM 2.5, PM10, CO, NO2 and O3 showed positive skewness. Severe pollution episodes were present in the dataset. PM 2.5 had strong upper and extremes. Spatial findings. Urban stations showed slightly higher PM 2.5 levels than suburban stations. Dongxi and Guiyuan had stronger central PM 2.5 values. In temporal findings, winter had the highest PM 2.5 variability and extremes. Summer generally showed lower PM 2.5 levels. Average PM 2.5 peaked in the evening, especially around 8 o'clock to 9 o'clock. Interpretation. The dataset showed clear spatial, seasonal, and hourly variation in Beijing air quality. Model building and critical evaluation. Target variable PM 2.5. Predictor variables. Numeric features year, month, day, and hour. PM10, SO2, NO2, CO, O3, temperature, press, DWP, rain, WSPM is weekend. Categorical features. Station, WD, season, day of week. Pre-processing strategy is numerical pipeline. Median imputation, standardization, critical pipeline, categorical pipeline. Most frequent imputation, one hot encoding. Models evaluated in this linear regression, random forest regression, gradient boosting regression. Critical justification is that linear regression provided a baseline while ensemble models were more suitable for capturing non-linear environmental relationships. After that, model performance and final selection. First one is the regression model performance comparison, and the second one is the predicted PM 2.5 for the random forest model. Final model selection. We use the best baseline model random forest. Tuned random forest did not outperform baseline. Final selection selected model untuned random forest regression. Model interpretations are strong actual versus predicted alignment. Most important predictors are PM10, CO, DEWP, SO2, temperature. Application development. In this, we can use it in Streamlit application. The developed platform was interactive Streamlit application. Application structure was dataset section, dataset shape, dataset preview, column names, summary statistics. Visualization section PM 2.5 by station, PM 2.5 by season, average PM 2.5 by hour. Correlation heat map. Model output section. Model performance table. Selected best model. Feature importance character. Short interpretation. Integration with the project. The application translated the notebook based analysis into a user friendly interface, allowing project outputs to be explored interactively. This is the link for the Streamlit app, which application which I developed. This is the this is the interface of the app. And I will show the app. This is the Streamlit app, Beijing Air Quality Analysis application. It's the dataset selection, dataset overview, preview of dataset, and the column names I used. And this is the summary statistics. In left, we can go visualization section. At present, we can see PM2.5 distribution by station, and we can change it here PM2.5 by season. This is the distribution by season, and we can change it by hour. Average PM2.5 by hour of day. This is that. And we can see correlation heat map also, pollutants and meteorological values. And we can check model output section also. In this model performance summary, we have selected best model, top feature importances, model interpretation. PM10 was the most important predictor of PM2.5, followed by CO. This suggests that particulate matter and combustion related emissions played the strongest role in prediction. And we are here in my GitHub. I uploaded everything. This is the libraries pynb file, and we can have the code here. In this, we have distribution of PM2.5, distribution of PM10, distribution of NO2, distribution of CO, distribution of O3, distribution of temperature, distribution of press, distribution of rain, distribution of WSPM, blocks plot of PM2.4, 2.5, block spot of PM10, block spot of CO, distribution of PM2.5 categories, good, moderate, unhealthy for sensitive group, very healthy, unhealthy, hazardous. And after that, we have PM2.5 versus temperature, NO2 versus O3, PM2.5 versus wind speed, distribution by station PM2.5, PM2.5 distribution by season, average PM2.5 by hour of day. And we have the correlation heat map of pollutants and meteorological variables, pair plot of selected variables PM2.5, PM10, NO2, CO, O3, temperature. It's the average PM2.5 by station and season. This is the actual was predicted PM2.5 with random forest using top 10 features importance. PM10, CO, DEWP, SO2, temperature, NO2, press, day, season by spring, O3. And we use the in app Dongxi, Guian, Changping. Here the project includes data import and merging, data cleaning and pre-processing, exploratory data analysis, machine learning model building, Streamlit application development. The Streamlit app contains dataset selection, dataset section, and visualization section, model output section. And this is the code for app. I will upload it in GitHub. It have everything about the assignment and app, everything. These are the requirements for this application Streamlit, Pandas, NumPy, Matplotlib, Seaborn, Skitlearn. And the conclusion, critical reflection and version control is actionable recommendation, strengthen monitoring during winter and evening peak periods, focus forecasting and intervention on variables strongly linked to PM 2.5, especially PM10 and CO. Expand the application to support more interactive analysis features. Challenges and limitations we face, missing values in several pollutant variables, extreme outliers in pollution measurements, Turner random forest did not outperform baseline model. Streamlit app currently has limited chart options and no prediction interface. Areas for improvement. Test additional advanced models. Add user inputs and forecasting options to the application. Improve respiratory structure for clearer project separation. In version control reflection, we face GitHub. We use GitHub was used to manage project files and commits. Descriptive commits improved organization and traceability. Version control supported structured development of the notebook, app, and supporting files. This is the GitHub commit history. That's it. Thank you all.